So I'm Dana now from the University of Maryland, and I guess you all know what the tutorial is about. Originally, the tutorial was going to be presented jointly by Malik, Ghallab, myself, and Paolo Traverso. About a couple of months ago, it became clear that Malik was not going to be able to be here because of some personal and family reasons. So we reorganized things so that Paolo and I would do the presentation. And then just last Friday, a few days ago, Paolo had a medical emergency, and he had to cancel the trip. He's doing okay, but they told him he had to stay in Trento so that they could do some medical examinations on him. So luckily, I have taught all of this material before in a class, so I'll be doing the whole thing myself. All right. Source materials for the tutorial is based on some portions of a new book that came out in 2016 on the subject of automated planning and acting. If you want to buy the book, that's fine, but you don't have to. You can download the final manuscript of the book at this website. It's not typeset the same way as the book is, but it has the same material in it. Also, some lecture slides that I prepared for the book you can get there, and all of the lecture slides for this tutorial are currently there. Okay? Another comment, I depend a lot on questions. If people don't ask questions, then I won't know what you're understanding and what you won't, and there's a good chance that I'll either start explaining things too slowly or too quickly. So please let me know if you have questions about anything. Does anybody have any questions? No? All right. Since several of you just came in, perhaps I should repeat the announcement that I just made. Malik is unable to be here because of some personal and family reasons. Paolo was going to come, and the two of us were going to split the lecture, but just a few days ago he had a medical emergency, and he's doing fine, but he has to stay in Trento this week so that they can do some medical tests. I'll be doing the whole thing, but it's okay because I know all the material. All right, so motivation for the tutorial. Well, first a definition. By an actor, we mean an agent that performs actions. And it incorporates a couple of deliberation functions. One is planning, which is coming up with what actions to perform. The other is acting, which is figuring out how to perform those actions. The traditional AI view of this is that the acting part is relatively trivial, that it's just execution. And it doesn't really require any deliberation. Well, that sometimes is correct, but often it is incorrect. And I want to give you an example now to illustrate this. Actually, here's an example where it's probably correct. If I can get the thing running. There we go. So this was a demo of Kiva Systems, which has been bought by Amazon, so it's now Amazon Robotics. This is one of their warehouses, and these robotic platforms are carrying the cases, the cabinets, to humans who then take whatever the next thing is that they have to take out of the cabinet in order to prepare the order. And the robot platforms simply bring the cabinets to people in the right order. Here, planning basically is just execution. The robots are going on tracks, electrical tracks that are painted on the floor so that they don't have to do any visual navigation or anything. And basically the entire warehouse has been engineered so that there's no need for deliberation on the part of these robots. Anything that requires deliberation is done by the humans. Okay? So that's a case where the execution assumption is correct. Here is another thing. It's a demonstration of a case where treating acting as execution is not correct. This is a Caledonian crow trying to get to a bucket full of food that's down there at the bottom of that pipe. And it's using a piece of wire to try to grab it. And it tries a number of times, finally realizes it's not going to work that way, and figures out how to use the side of this tub as a brace for bending the wire into the shape of a hook. And keeps doing it until it's satisfied with the hook, which will be in another moment. And voila, it gets the food. And I believe that is something that the crow figured out how to do itself. Whether this particular one did, I don't know, but there have been birds that have figured that out. So there were a number of actions that this bird performed. It had to do some pretty serious deliberation in order to figure out how to get those actions to work. All right? Okay. So a little bit more about the definite difference between planning and acting. Planning normally depends on prediction and search. The prediction uses models that talk about what the actions will do. So these are descriptive models. And the search is done over predicted states of the world and possible ways to organize the feasible actions. Different types of actions are available in different kinds of domains. These will require different kinds of predictive models and therefore different planning problems and different techniques for solving those planning problems. Some of these are the subject of a lot of work in areas such as robotics or various engineering disciplines. What most AI planning has concentrated on is the planning of these symbolic level tasks to carry out. Okay? But the techniques here are a little bit different than the techniques here. Acting deals with the fact that the actor, like that crow, is situated in an unpredictable environment. That environment was not dynamic, but often the environment is. There can be things happening while you're carrying out the action. So you need to adapt the actions to the current context and react to events as they occur. And so that's going to rely on a different kind of model. Before we had descriptive models, now we have operational models of the actions, which don't predict what the state of the world will be like after carrying out the action. Rather, they tell you how to perform the action. So it'll depend on that and on observations of the current state. So planning will predict things, acting will then carry them out, and you get this interrelationship like that. All right? Any questions so far? Okay? So some general characteristics of the interrelationship between planning and acting. One is that typically there need to be multiple levels of abstraction. Actors are generally organized into physical subsystems at various levels, and the deliberation has to reflect this. Second, that deliberation has to be heterogeneous often, because these subsystems use different techniques, sometimes in different subsystems with the same level, or sometimes in different levels of the hierarchy. Finally, the planning needs to take place continually, and it needs to be done online. You can't plan everything in advance because the plans... Hold on a second. I know I changed that slide. Let me see if I have the right one here. Sorry about this. That is very strange. I'll keep going. Sorry about that. What I had intended to say here, and I was sure I had changed the slide to reflect it, is that you can't plan everything in advance because not all of the information that you need in order to do the planning is available in advance. And so the plans are going to remain abstract and partial until more detail is available. Okay? I don't know why that correction isn't there, because I'm sure I did it. I guess another example of the interrelationship between planning and acting. And if it's not on the slides that are on the web, I will correct it and repost them. All right? Okay, so I talked about different levels of abstraction. Here's a simple example of a robot that's performing actions and respond to user requests, and there's a request of bringing some object to a particular room. In order to do that, it has tasks such as going to the hallway, going down the hallway to wherever room 1 is, fetching the object, going back to room 2 and delivering the object. In order to go to the hallway, it has to go to the door, open the door, get out and close the door. And finally, down here at the bottom, in order to open the door, there are these low-level tasks such as what kind of door is it, motion planning to get close to the knob, grasping the knob, so forth. The planning activities tend to take place at the higher levels of a hierarchy like this. The acting activities tend to take place at the lower levels. All right? So, outline of the rest of the tutorial. First is the introduction, which is what I'm nearly done with right now. Second, some deterministic models, including refinement methods for acting and for planning. Temporal models, where we have timelines and temporal refinement and the use of chronicles. Non-deterministic models and how to do the reasoning about non-determinism both offline and online. And a little bit about some work with input-output automata and refinement methods in this domain. And then finally some conclusions. And then just as a reminder, if you want any of these slides, here's where you can download them. All right? So, I mentioned that this was related to the book. The tutorial covers part of Chapter 3, part of Chapter 4, and part of Chapter 5. There's a lot more detail that I won't have time to go into today, but that's the part of the book that it concentrates on. Also, the cover of the book, people have sometimes asked about that. This is a picture called The Conjurer. It was done by Hieronymus Bosch in the 15th century. And the reason that we chose this, Malik Ghallab was the one who advocated this, and he talked Paolo and me into it. His point was, there's a lot of acting going on in this picture. So, any questions? All right. In that case, I will continue on to part 2. Before I do this, no, that's not there. Okay, never mind. It just troubles me that change that I made to the slide somehow vanish, but don't worry about it. Okay, so refinement models. Motivation. As I mentioned just a few minutes ago, we have the multiple levels of abstraction and the planning needing to be done continually and online along with the acting. So let's go to this bottom level that I had in this example where we are opening the door. And the first task I had here was identify type of door. The reason why is, in order to do the action of opening a door, there's a continual interaction that goes on with the environment. And how you go about opening the door depends on what kind of door, and often that is something that is not known until acting time. All right? So, one question would be, is it a sliding door or is it one that rotates on hinges? If it rotates on hinges, then are the hinges on the left side or on the right side? Does it open toward you or away from you? The thing that you grasp in order to open it, is it a knob or is it a lever or is it a push bar or is it a pull handle or is it a push plate or is it a fish? The point is that for all of these variations, you need to open the door in a different way. And that's something that you have to figure out while you're doing it. Okay? So I'll talk about a representation that we'll use as the basis for both some acting and some planning. The representation is based on state variables. An acting algorithm a planning algorithm, and some techniques for combining the two. Okay? So, how many of you are familiar with state variable representation? How many of you are not? Okay. I'll go through a quick review, which will hopefully be enough to bring everybody up to speed without boring the rest of you. What most of you are probably familiar with is classical representation, in which you represent states as sets of logical assertions, logical atoms that look like these. Well, some of these logical atoms represent properties that are rigid. They don't change. In this example here, we have these robots that are going around from one loading dock to another on these little bitty roads that connect them. We don't have any action for building new roads or for destroying existing roads. So the adjacency information, which of these loading docks is adjacent to the others, that's rigid information. Okay? On the other hand, the other properties are things that will change as the robots perform their actions. Where the containers are that they're picking up, where the robots are. Okay? State variable representation, we're still going to use logical atoms for the rigid properties, in this case the adjacency information. And for the varying properties, we're going to use state variables. A state variable is a syntactic term, like the location of robot 1, or the whatever the cargo is in robot 2. And they can have values assigned to them, and they're going to have different values in different states. Okay? So it's kind of like a field in a record structure, but it's a variable you assign a value to. All right? Okay, a task is an activity for the actor to perform, and for each task there's one or more refinement methods. These are operational models that provide different ways of performing the task. And the syntax that we're going to use for those looks like this, where you have a name for the method, you have an argument list, you have the keyword task, and then whatever the name of the task is that this method can be used for, and whatever the arguments of it are. Okay? And a precondition test, and then the body of the method is a program. And this program can contain the usual kinds of things that a computer program can have in it. Assignment statements, control constructs such as if, then, else, while, for, so forth. Tasks to perform, goals to achieve, and finally, commands to the execution platform, which is the thing that will actually execute the low-level actions. Okay? So this is a method for achieving a task. You can also have a method for achieving a goal, or a method for responding to events. There's some minor differences among these three, and I'll talk a little bit more about that later. But for now, let's concentrate on these. Okay? So here's an example. We have a robot here. It's at location 0, and we've given the robot a task of fetching container C2. Well, in this diagram we can see where container C2 is, but the robot can't. Its sensors only work locally. So what it's going to have to do is search the various locations in order to find C2 and then bring it back. Okay? So we have the task of fetching the container using a particular robot. In this simple example, we only have one method for that task. That method has no preconditions. The body of that method is a program that looks like this. If the robot doesn't know where the position of the container is, then it has the task of searching for it. That's another task which has another method that we'll talk a little bit about down here. Otherwise, if the robot does know where the container is, well, if where the container is the same location where the robot is, then the robot has the action of taking the container. Otherwise, it's going to move to where the container is and then take it. All right? Okay, searching for the container. One method for that, again. the precondition for using this method is that you don't know where the container is. Otherwise, it doesn't make any sense to search for it. The body, well, you have a number of locations that you might be able to look at. We're assuming here that the world is static. Obviously, that's not going to be true in general, but it's going to be true in this simple example. And so if you've seen something at a particular location, it's going to stay there. All right? So that's our working assumption here. So now, if there exists a location somewhere in your domain that you haven't looked at, that's what this says. The view variable has a value false for that location. Then go there, look to see what is there. If what you see is that the container you're looking for is there, then take it. Otherwise, recursively, keep searching. And so this would be a recursive call to the search task. You would then use the same method on that, and it would look at another location that you haven't looked at. Okay? If you reach the point where you have looked at all of the locations and haven't found the container, then the else clause is that you fail. Okay? Any questions about that? Okay? So I said there's a little bit of a difference between methods for tasks and methods for goals. We're going to write a goal as a special kind of task, achieve some condition that needs to be true in some state of the world. Okay? And the method is going to have pretty much the same syntax, except that, again, the task name is going to be achieve of something. There is going to be a difference in how this method is carried out. During the execution of this program, if the condition that you're trying to achieve becomes true before you finish executing it, well, then you don't need to finish executing it. You've achieved what you needed. All right? So this sets up a monitor that will look to see whether that's true and execute from that if it becomes true. All right? Alternatively, if you have finished executing this program, and even after executing it, the condition is not true, then you fail. Okay? Events, well, instead of saying task, we say event. The rest of the syntax is the same. You have an event name and arguments. An event is simply something that can happen in a dynamic environment. Okay? And so at that point, you may need to figure out how to respond to it. For example, if it's an emergency, then you might have a method that says if you're not already handling another emergency, then stop what you're doing and go handle it. Okay? Any questions about any of that? All right? So that finishes with the representation. Next I'll talk about an acting engine called Ray. It's a generalization and formalization of a system called OpenPRS. How many of you are familiar with a venerable system called PRS, done by Michael Georgioff a bunch of years ago? OpenPRS is an updated version of that, which is available as open source. It's been used in a bunch of robotics projects, particularly in the research lab where Malik works. And this formalizes some of this stuff that's in this program, and it also generalizes it. The input consists of a collection of external tasks, things that are coming in from users or wherever, goals and events, and the current state. The output is commands to the execution platform. Okay? And then the execution platform can send back information about what the current state is. The thing can handle multiple tasks, goals, and events simultaneously. The way that it does that is for each of them it has a refinement stack. Basically it's like a runtime stack for a computer program. Just like you have routines calling subroutines, here we're having tasks that invoke methods, and so you have these things build up. And I'll go through an example of that in a minute. All right? So you have an agenda then that consists of all of the current refinement stacks for all of the tasks, goals, and events that you're working on. All right? So the basic idea of it, here is the pseudocode for it. We go around in a loop where we do something. What is that something? It is you look to see all of the external tasks that have come in since the last time you went through this loop. And for each of them, you look for the set of method instances that are applicable. Arbitrarily choose one of them. I'll talk more about that in a minute, or in a few minutes. Create a refinement stack, saying that you have that task you're trying to accomplish and you're going to use this method instance for it. Add it to your agenda. So you do that for all of the external tasks that have come in, things that have come in here. Then once you've put all of them into the agenda, then you look through everything that's in the agenda, progressing each member of the agenda by one step. If you've finished with it, you remove it from the agenda. Otherwise, you keep it there. Once you've done that for each one of the stacks, then you go back and look to see if anything new has come in. Okay? So, progressing a stack, what does that consist of? There's some complicated pseudocode for that in the book, but basically it's a simple decision tree. Looks like this. You have your stack, you look at the current step that you've sent to the command platform. Remember, these methods will send things to the command platform. It may, or the execution platform. It may take them a while to finish the action. And so you start that action running, and then you look periodically to see if you're done. All right? So you check the status. If it is still executing, then you've done everything you can to progress that particular stack. You go around in the loop, looking at the other ones. It might have failed execution, in which case you have to retry it. And there is a sort of a variation of this for retrying things that have failed. Okay? Also, anytime I say task here, it could be a task, it could be a goal, it could be an event. I just didn't want to have to keep rewriting that. Okay? Otherwise, if it is finished, then you look to see, well, in the body of the method that you're currently executing, are there any more steps? Well, if no, then you're done with that particular method and you pop it off of the stack. All right? Otherwise, you get the next step, look to see whether it is a command, in which case you send it to the execution platform, an assignment statement, in which case you update your current state information, or a task, a goal, or method, in which case you look at the available method instances, and you do the same thing with putting them on the stack that I talked about up here. All right? Any questions about that? Yes?
If you're just going through each of the stacks in the agenda,
yes.
What if you have conflicting goals? Like if you have a location you need to go to for one stack and a location for the other, where's the reasoning that handles that?
That is something that you would have to put into the methods in order to implement that. It doesn't do any specific reasoning other than what I told you about in the code in the flowchart. Okay. All right? Other questions? Okay. Yes?
So events come in as new tasks then at the top of your loop?
Yeah.
So
well, events could come in here as things, say, that are given to you by other actors or by human users. Alternatively, there might be things that get sent back from the execution platform. Okay?
But they're treated identically.
Yeah.
Being a new task.
Yeah. Other questions? Okay. What I'd like to do now is to go through a very simple-minded example to show you how this works. So the example is fetching that container, like I was talking about earlier. Okay? So you have the task of fetching it. We have our fetch method, which I told you about. And what I'm doing here is I'm drawing a refinement tree. The refinement stack gets built from the bottom up. The refinement tree is going to be top down. So this is basically going to be bottom up, the current path through the refinement tree. Okay? So we have the task, we have the method for it. The method now invokes this task of searching, where we have another method for it. All of these things are going on this refinement stack down here, but I'm really going to pay more attention to the tree. We have the method of searching. Now in the body of the method, suppose we've already moved to the location. Now we send the perceive command to the execution platform. And now let's just suppose that there's something wrong with the robot sensors. They're not working, so there's a sensor failure. Okay? So perceive fails. Well, if perceive fails, you can't do the rest of this method body. So this method body fails. This method fails. At that point, you say, are there any other methods or method instances that are applicable to this task? You look around for others. If there are any, then you take one of them and you start executing it. Otherwise, if there aren't any of those, then this method would fail, and you'd have to look and see whether there's any others available for this task. So this looks a little bit like backtracking. It isn't quite backtracking, and the reason is that in a backtracking program, you basically exit from what you were planning to do, and you haven't actually done anything, so the state of the world hasn't changed. Here you've executed some actions. All right? So the state of the world has changed, and you're not going to backtrack out of all of the actions that you performed. You're going to keep going from where you are. All right? Okay, so that's the acting engine. Next, planning. Motivation here is when dealing with an event or a task, Ray may need to make either or choices. There might be several different methods that are available. There's a question of which one to use. There might be refinement stacks for several different tasks. And I here use the simple-minded notion that we're going to progress each of them a single step and then we're going to go around in the loop again. Obviously, that isn't always how you want to do it. Some of them may need to have higher priority than others. And so there's some questions about how you're going to prioritize them. Okay? Well, Ray makes its choices reactively. It's not doing any look ahead. And so if it makes a bad choice, that could be a costly thing to do, or it might even be irreversible if you have a domain where there's some dead-end states. So what we would like to do then is use a planner to look ahead, explore the possible choices, predict what will work well and what won't. Okay? So refinement planning, there's an algorithm called SERPE for that. The pseudocode for it is in the book. I'm not going to show you the pseudocode. The basic idea is, well, I already showed you the Ray algorithm. We're going to simulate it. Okay? So we're going to simulate it. For each command, the commands are the things that get sent to the execution platform. Rather than sending them to an execution platform, it's going to use a descriptive action model to predict what that command would do if we invoked it. It's not going to tell you how to carry out the command. It's just going to tell you what it would do, or try to predict what it would do. And then we do a heuristic search through the possible alternatives. If you have different possible method instances, that may lead to different refinement trees. And you can simulate what would happen in each of them and explore the consequences. Okay? This is a generalization of hierarchical task network planning. And there was an algorithm that I and some of my students developed for that a long time ago called SHOP. The way that it is similar, in SHOP, the body of a method was not a program, it was a list of tasks. And you plan for each of those tasks. Okay? And since you know in advance what this list is, you could actually do some reasoning about the tasks if you wanted, and use that to help figure out how to plan things. In SERPE, you don't have this. SERPE is using the same methods that Ray uses. And so the body of a method is a program that is going to generate the tasks. You don't know what the next task is going to be until your code generates it for you. And if you are going to backtrack, like I was talking about doing up here, you need to backtrack over the program execution. So implementing this turned out to be a considerably more complex thing. All right? Okay, here's the basic idea. You non-deterministically choose a method for your task. You progress that method repeatedly until it's finished. We're only doing this for one task. We don't have the multiple tasks like Ray did. We're only going to look at one at a time. All right? So you progress it until it's finished. Here's that same progress thing that I had up for Ray. It's like calling this thing repeatedly. The main difference is that instead of triggering a command, you use your action model. Okay? And here, rather than making an arbitrary choice like Ray did, here I said we arbitrarily choose one of the candidates. That's because we can't backtrack once we've made that choice. We've made a commitment. If we're doing something like a backtracking search or an A-star kind of search or whatever, that's something that you can go back and re-examine, backtrack from it. So the typical way in a lot of textbooks for representing that, if you don't want to talk about the specific mechanism that you're using to decide which backtracking thing you're going to do in what order, or whether you're doing A-star or greedy best first search or what, is to call it a non-deterministic choice. Okay? So, where was that? Oh, sorry, I went too far. So the theoretical model for that would be you have a bunch of possible choices. The algorithm doesn't specify how to choose them. And you could consider the idea of having a non-deterministic Turing machine that's going to look at all of them in parallel. But if you implement that as a deterministic algorithm, then you could use backtracking, you could use A-star, you could use a bunch of other things. Okay? Okay, so I'll give you an example of this. Let's take the things that we used for Ray making the search earlier and write descriptive action models for them. We're going to run into a problem, and it's already written on the slide, and I'll get to it in a minute. We're going to use precondition and effects representation, just like classical planning operators, except we're going to use state variables, of course, instead of the logical atoms. Okay? So our action model for the robot taking an object at some location L is the cargo that the robot was carrying needed to initially be nothing. It needed to be at the same location that the object that it's picking up is. The effect is that the cargo that the robot's carrying is now that object, and the location of that object is now the robot. Okay? Putting down is basically the inverse of that thing. Sort of the obvious preconditions and effects. Now, here's where we get into trouble. Perceiving what is at a particular location. Remember, this is supposed to predict what the action is going to do. If we knew in advance that when we perceive at location 3 that the container that we're looking for is going to be there, then we wouldn't need to do the search in the first place. We would just go directly to that location and pick up a container. Okay? So, we can't do this fetch example. As simple as it was. What I'm going to do instead, first is to talk a little bit more about why. Anytime we have a model of the environment, inherently that is going to be incomplete. The traditional solution that people have looked for in the AI planning community is to say, well, let's have a non-deterministic model in which we have all of the possible alternatives, and we look at all of them and assign expected utilities or whatever. Even if you have a non-deterministic model, it's very, very unlikely that you will have thought of all of the alternatives that could occur in a complicated real-world scenario, such as the entire segment of road in front of you collapsing. Okay? So, you can't always predict everything, even with a non-deterministic model. The techniques that I'm going to talk about can be extended for non-deterministic models, and I'll say a little bit about that in part 4 of this presentation. If you use deterministic action models, you get a much simpler planning algorithm, and it's okay to use it even in domains that are non-deterministic, as long as those errors are infrequent, and as long as when they occur, they don't have severe consequences, like a car going into the hole. Okay? So if that's the case, then remember I talked about how we have to do the planning online. In that case, it would be feasible for the actor to recover online. Okay? So here's a simple deterministic example. We have a robot that can move among these various loading docks. It can pick up containers, move them to other locations. We have the sort of usual precondition and effects representations of loading something onto the robot, unloading it off of the robot, and moving to a different location. Does anybody want me to go through the details of those? Okay. I'll assume you all know what those look like then. And we have an initial state of the world, which again is sort of the obvious thing. You're probably used to seeing it with logical assertions. Here we're saying the same thing, it's just with state variables. Okay? All right. So we have the task of putting container 1, which is right here, into pile P2, which is this pile here that already has a couple of containers on it. Okay? We have a method for putting something into a pile. The precondition is that it needs to be, sorry, I forgot what I had on the slide. Give me a moment. We have two methods for putting something into a pile. One of them is the method that you use if the thing you're trying to accomplish is already true. If we're trying to put this container into this pile, and if this container is already in the pile, then we don't want to do anything. Okay? Another method for the case where the container is not already in the pile, and in that case, you need to know what pile it's in, etc. And you need to have your robot not carrying anything already. The body of the method says if the robot is not at the location where the container is, then go there. Uncover the container. What that means is if there's anything else on top of it, you remove it. Load the thing onto the robot. If you're not at the location where the container needs to be, then go there and unload it. Okay? Uncover, I'll get to in a minute. In fact, we'll get to it now. Uncover is again sort of the obvious thing. Two methods for it. First is if you're trying to uncover container C and it's already at the top of the pile, there's nothing on top of it, then you don't want to do anything. Okay? Otherwise, you take the top thing off of the pile, put it elsewhere, and then you recursively have another uncover task. So I omitted that, but that's basically what it is. Okay? So, okay. We're also developing a refinement tree as we go through this. What happened? I got ahead of myself. We have this task of putting this thing in the pile. We chose to use this particular method because this thing is in a different pile from where it's supposed to be. This method, if we start executing it, has this uncover task, which is why we retrieve that. And so we use this method. There's nothing that needs to be done, so there's no children of that in the tree. Okay? So next we come to loading it onto the robot. Well, that is primitive action. We have our descriptive action model for it, which basically says the container is now here rather than in that pile. Okay? Next, we have to navigate to where we're going. Again, that's a primitive action. It's a method that decomposes into primitive action. Don't worry about that. Anyway, at the bottom we have a primitive action that moves us here. Okay? Next, unload. Well, that's another action. We unload it onto there and we're done. Okay? So this basically sort of scripted for us what we need to do. All right? Any questions about that? All right. So some heuristics for this. I said that we non-deterministically choose a method, and I said that that was shorthand for saying we're not sure how we're going to do it. What heuristic function might you use? Well, that's still kind of an open problem, and something that might be an interesting thing to do research on if any of you get interested in this stuff. In some cases, classical planning heuristics can be used. In other cases, they become intractable. There was a paper that was done by Shiva Shankar and a few other people that appeared at ICAPS 2016 on that. Various ad hoc approaches that you can use that are typically going to be domain specific. You could try the methods in the order that they're given in whatever your knowledge base is. You could use some domain specific estimates, which you might like to do since you're writing these domain specific methods anyway, or you might even keep statistical data on how well things have worked in the past. Okay? But I don't have any final answer for you on that. Next, how to use planning in acting. How are we doing on time? We're halfway into the break period, aren't we? No, it's not until 3:30. Never mind. Got ahead of myself. Okay, using planning in acting. The book describes two approaches for that. One is an algorithm called REAP, which is basically a Ray-like actor that uses SERP-like planning whenever it needs to make a choice. That algorithm is very complicated. I would get all of you confused if I tried to explain it. I'm going to skip it. Okay? What I'm going to do instead is I'm going to have a simple, very dumb, non-hierarchical actor that uses refinement planning in order to make its choices, and that'll illustrate the basic issues. Okay? So it's called Run Look Ahead. What it does is it looks at the observed state. As long as that observed state doesn't satisfy whatever goal it's trying to achieve, it calls a look-ahead algorithm, which is basically a planner, and that returns a plan, pi. All right? Well, if what it actually returned was failure rather than a plan, then we've failed. We can't get there. Otherwise, it takes the first action in that plan and performs that action, and then it discards the rest of the plan. Goes back around in the loop, calling the look-ahead planner again, getting a plan, taking the first action of that plan, executing it, discarding the rest of the plan, so on. So the look-ahead algorithm that we have is a modified version of SERP that will search part of the search space and then return a partial plan. The reason that Run Look Ahead executes the first action then calls Look Ahead again, if we're only going to search part of the search space, if we are not going to search, say, all the way to the goal or all the way to the task completion, we can't be sure that we're planning the right thing all the way into the future. Okay? So we execute an action, we get a little bit closer, we might be able to make a more informed choice the next time. Any of you who have looked at computer programs that play chess, they do something very similar. They search ahead some number of steps to try to figure out what's the best thing to do. They discard all of that search except what it says is the first action. Execute that, and they do the search all over again. Okay? Well, a potential problem with that is that you are going to have to pause repeatedly while waiting for the look-ahead planner to return. That ends up being a problem in things like Minimax game tree search. And in fact, a skilled human will sometimes do something that is deliberately a little bit strange in order to get these programs out of a place where they can make decisions quickly and into a place where it's going to take them more time, and so they're more likely to run out of time. So anyway, if you're waiting quickly, you're doing this in a dynamically changing environment, perhaps. What do you do if the environment changes during the wait? Okay? So, well, another possibility would be, rather than waiting for the look-ahead each time, let's simply keep performing out of this plan as long as it's working. And we only call the look-ahead planner when it really becomes necessary to. So that's called Run Lazy Look-Ahead. Same kind of loop as before. As long as we're in a state that doesn't satisfy the goal, we call look ahead. If it returns failure, then we return failure. Otherwise, what we're going to do is we're going to go around in a loop where we repeatedly pop actions off of that plan until one of three things happens. One is that maybe we reach a point where we finish the entire plan. Remember, this is a partial plan. It hasn't gotten us necessarily all the way to the goal. We might have finished it. Or we might reach a point where the goal is now satisfied, in which case we're done. Or we might reach a place. Here's one of the things that you can do if you are just keeping this plan rather than calling a look-ahead planner. Since you have just this one plan, you might be able to do some more detailed look-ahead just on that plan. For example, if you're executing in a physical environment, you might use a physics-based modeler. There exist such things for predicting the outcomes of actions in a more detailed fashion than you would be able to do in this look-ahead algorithm where you're having to look at all sorts of plans. Okay? So you might want to do that. So until one of these three things happens, you simply keep executing the plan. And once you reach a point where you exit this loop, then you go back up to the top of the loop. If you've satisfied the goal, then you exit. Otherwise, you call the look-ahead planner again and you start doing the same stuff again. All right? Any questions about that? Okay. One potential problem with this is sometimes you can wait a little bit too long to replan. You may have a plan that says you're okay going along in this direction, and then something went wrong. An exogenous event happened, or maybe some accident occurred in one of the actions you're performing that's going to invalidate the rest of your plan. And you keep executing it, not realizing you're in trouble, because the actions that you have, the first few of them are still executable. That's one of the reasons we want to try to use this simulator, is to predict in advance when a failure is going to occur later on in the plan we're currently executing. Okay? If we don't do that, we may not notice problems until it's too late. Okay? Or sometimes things can happen that will create new opportunities where you can find a better solution. In that case, you might be interested in replan. And it'll miss that as well. Okay? Okay, here's a third alternative, which is kind of intermediate between the other two approaches. Oh, something is badly wrong. I was complaining earlier about having old slides. I know I deleted that duplication as well. Okay. Something went wrong with my backup procedure. I don't know. I'll just keep going. I know the material, so even if the slides are wrong, I can keep telling you about it. Run concurrent look ahead. It runs the look ahead planner and the plan executor in parallel with each other. So here we go through a loop where we're simply calling the look ahead algorithm again and again and again. All right? Here we go through in a loop where we take whatever the current plan is from our latest call to the look-ahead planner that is returned. We pop the first action off of that and we perform it. All right? And then we go ahead and look for the first action again in whatever the current plan is. If the current look-ahead hasn't returned, then it'll be the same plan we had before. We just take the next action off of it. On the other hand, if our look-ahead planner has returned, then it might be an action in a different plan. We take that instead. Okay? Obviously, there's some synchronization primitives that you would need to, in order to get this to work right. But that's the basic idea. Okay? It avoids the problem with waiting for the look-ahead algorithm to return, because if it hasn't returned, it'll keep using the plan that it has. It may detect some problems and some opportunities earlier than run lazy look-ahead would be, but it might miss a few that run look-ahead could find. Okay? Any questions? All right. So how do we do the look-ahead? I said we have a modified version of something like SERPE that's going to do a partial search. Well, there's several alternatives. One is something called the receding horizon approach. The idea is that you search to some fixed depth. You cut off this search before you get to your goal or finish your task. It might be a bound on your search depth. It might be a bound on how much time you're willing to spend. And the reason it's called receding horizon is that you search to this depth. Your actor then is going to execute part of the plan that you've returned. You're going to search to a fixed depth again. Your actor is going to execute part of that plan, and you keep going. Okay? So each time you make these successive searches, your horizon is farther on. Okay? Sampling. The idea there would be to try a few presumably randomly chosen depth-first rollouts that go all the way to the end, where you're looking to something that may get you to a goal, but you're not looking at all the possible alternatives. Okay? And if one of them looks like it's okay, you just use that, and you haven't searched the entire space. Third possibility would be sub-goaling, and the idea there is that instead of planning for our ultimate goal, we at our top level, decompose it into some sub-goals. We call the planner on one of them. We execute that plan until it's done. We call the planner on another one. We execute that until it's done, and so forth. Okay? And you can use combinations of these as well. And here's an example of it. This is a game called Killzone 2. Video game that was released in October of 2009. I didn't learn about it until 2012. What happened was that someone took my shop HTN code, which, remember, I said that Serpe does a generalization of that, and implemented a version of it that plans the enemy actions at the squad level. This is one of these first-person shooter games where you're playing against enemy. All right? And you're trying to shoot them down, and they're trying to shoot you down. And this thing is used to plan the enemy actions. What it does is a combination of sub-goaling and receding horizon. The way that works, it'll take some intermediate goal, like maybe you're shooting at one of the virtual opponents and wants to get to shelter. And so it comes up with a plan that's maybe 4 or 5 actions long for doing that, and it executes that. As you're doing that, the game is running the planner again and again and again, several times a second, as the state of the world changes. And so, therefore, if something changes that makes that plan not a good one anymore, it's going to react by coming up with a different plan. All right? The reason why this worked well is that how many of you would want to play a game like this if the game environment always won and you always lost? Anybody? Nobody? Well, that's the point. You don't want necessarily to get the best possible plan. What you want in this case is for it to generate actions that appear believable and appear consistent to human users, and you need to get them very quickly because it's an environment where things are changing very quickly. And that's what this provides. Okay? So that's an example of those techniques. Okay. Ray and Serpe themselves, they're new algorithms. We developed them while writing the book. We don't have any detailed publications about them elsewhere. Several of students in an AI planning class that I taught this semester had a term project of implementing them in Python. They aren't quite at the point where the code can be released yet. They're nearly finished, and we hope to make the implementations available so that people can experiment with them once they're done. But I do have a demo that they did with their current somewhat buggy version of the Ray algorithm playing the game Pac-Man. And if you want to look at it yourself, here's the URL for it. The student who did this is named Zheng Yan, and I wanted to give him credit for it. And I have a copy of it here, I thought. Give me a moment. There it is. No, that's not it. Okay. So, obviously it's a simplified version of Pac-Man. There's only one ghost. And the thing is a little bit of a kludge. I said that in Ray, the body of a method is a program which you can execute, and the program has actions embedded in it. Basically, this is all done in one method, and it just keeps executing, returning actions until it's done. Also, the strategy that it uses is not always the most intelligent strategy. Sometimes you'll see the thing going back and forth because it can't figure out what to do. Has that happened yet? There. But on the other hand, as something that a student did as part of a term project is pretty cool. And so finally it finishes the level without getting eaten by the ghost. All right? So that was done just in Ray. One of the things that we want to do as part of releasing the code, I've been talking with Zhang about implementing this as something with alternative methods where it could do a sort of a tree search to try to look ahead. And we hope to have that in place by the time we release this thing. Okay? So that is all in Python, so it should be easy for people to pick up and play around with. If anybody is interested, just send me email and I'll let you know if and when it becomes available. All right? So, summary of this part of the tutorial. I talked about the acting engine, Ray, and the main point about it is that the body of a refinement method is a simple program. It includes these commands of the execution platform. The refinement planning algorithm, which simulates Ray on a single task or event or goal. The limitation that it has is that it has to use deterministic action models. And then finally, the way that you combine these techniques. Are there any questions about this part of the talk? All right. In that case, let's see. Yeah, I should have time to start the next part, and I'll get about halfway through it by 3:30 when the break is, so that we can then take the break and I'll come back and finish this part. And this part is on temporal models. Just as an announcement for those of you who came in late, I'm doing the entire tutorial myself. Originally, it was going to be all three of us. Malik had to cancel a couple of months ago because of some personal and family reasons. Paolo had a medical emergency last Friday, and he's okay, but they wanted him to stay in Trento so that they could run some medical tests on him. Luckily, I've taught all this material before. All right, so motivation for temporal models. I'll start out with a few success stories. First one is the remote agent experiment. This was the first AI control system to control a spacecraft without human supervision. This was Deep Space One spacecraft in 1999. And a key component of it was the RAX PS planner and scheduler. Okay? Oh, I thought I had more on that. It may be again a case of the slides being out of date. Okay, anyway, it didn't control the spacecraft for the entire operation of the spacecraft. Rather, it did a portion of it simply as a test. The NASA people weren't willing to let it control the whole thing because they didn't know whether something catastrophic might happen. It worked fine. And it was because of this success that they ended up using the AI programs in a much bigger way in the Mars rovers. Okay? Second, ICAPS. This was something done by my colleague Malik Ghallab and some of his people in the early 1990s through the early 2000s. And he has a video of it, which I think I can start running. It's running very slowly. This is old technology. Sorry, it didn't look like it was running slowly, but that's because the thing was speeded up. You saw that person go by very quickly. The point is that it is developing here a temporal plan. It is doing some things with tasks that it wants to accomplish and actions that it needs to do to carry out those tasks. But it has durations associated with these, and it often is doing several things in parallel with each other. Okay? I'll go on to the next one. T-Rex and Casper. T-Rex is a system developed by one of the former NASA people for an oceanographic research institute between 2005 and 2010. And it uses some similar kinds of temporal planning techniques for undersea vehicles. And Casper is an ongoing project at NASA JPL, which is going to, actually I don't remember what it's going to do. Does anybody in the room remember? Okay, sorry, that's one part I don't know. Anyway, the point is that the common characteristic of all of these is that they use an explicit representation of time. All right? So I'm going to talk about how to do that. We'll have durations associated with the actions. We'll have delayed effects and preconditions on the actions. For example, resources that can be borrowed or consumed during an action. Time constraints on our goals. These might be relative constraints or absolute ones. Exogenous events that are expected to occur at various points in the future. Information about when. Maintenance actions, which would be actions that you use to maintain some property over some period of time. And that's more general than just changing a value, because sometimes you may need to keep it the same despite events that are going on in the world, like you want to track a moving target or you want to keep a spring latch in position. Concurrent actions that can interact with each other, and I'll go through an example of that later. And delayed commitment, where you may want to leave some of the things undetermined at planning time so that you have some flexibility about how you do them at acting time. Okay? So, first concept that you need to know about is a timeline. Up until now, we have used what I'll call a state-oriented view of the world. The world is a sequence of states. We have instantaneous actions that transform each state into the next one. No overlapping actions. That was okay when we weren't paying attention to the amount of time these things would take. For a time-oriented view, what we're going to do is we have a sequence of integer time points, t equals 1, 2, 3, so on. The scale of these time points is arbitrary. It could be 1, 2, 3 milliseconds, 1, 2, 3 seconds, 1, 2, 3 minutes, whatever scale you want for what you're working at. For each of the state variables that we had before, we're going to have a timeline associated with that variable, saying what values that it has during different time intervals. And that's going to reflect, whatever happened to change its value at those times. And so now the state of the world at some time t is you simply look at all of your state variables. What are the values that they happen to have at that particular time? That is your state. Okay? So the orientation of a lot of this is on the timelines, and you can figure out the states from that. Okay? All right. So the planning is going to be constraint-based. You have various state variables. You're going to constrain their values at various time points or over various time intervals. How many of you are familiar with plan space planning? Also called partial order causal link planning. How many of you are not? Okay, one person. I will be giving a little bit of a review of the parts of it that are relevant. I won't talk about it directly, but I hope that the pieces that you need to know will become apparent as you need them. Okay? If you don't understand anything that I'm saying, please feel free to ask questions. Probably half of the other people in the room will be very happy that you did, because even though they know plan space planning, they may have trouble remembering some of the details. So, don't be embarrassed. All right. So, anyway, somewhat like that, except that we're going to have time durations, and we're also going to have task refinement. And we can have a complete plan in which the time points are constrained but not completely fixed. That's what can give us some flexibility. All right? Okay, so outline, representation that we're going to use, temporal planning algorithm called Templan, some ways to speed it up in terms of heuristics and such, and some stuff about acting. Okay. Oops. Wow. Okay. That happened to Sunadita yesterday, too. We must be using the same version of PowerPoint.
Yeah.
All right. So, I think that's where I was. Yeah. So a timeline is a pair, TC, where T is a set of temporal assertions and C is a set of constraints. A temporal assertion, there's two kinds. One is called a persistence condition. That is an assertion saying, damn, I don't know what happened to these slides. I promise you I fixed all these errors just yesterday. This is weird. Okay. Persistence and change are reversed on this thing. This is the persistence condition. It says that over some time interval, starting at T2 and going to T3, that the location of R1 is some particular value. Okay? So that remains the same over that time interval. So that's this green thing in the diagram over here. All right? This one should say change rather than persistence. It says that over some time interval that the value of a state variable changes from one value to another. Okay? So this one says it changes from loc1 to L. This one says it changes from L to loc2. All right? So these three things are represented in that graph over there as how the location of robot 1 evolves over time. C is a set of constraints that can include time constraints, such as the ordering on these time points, and also things having to do with the duration of the time intervals, something like saying the duration of this time interval from T3 to T4 is less than C plus 2, or C is some constant. Okay? The other kinds of constraints are object constraints. Something like saying this location here is something different from location 1 and is also different from location 2. And then finally, we may often talk about the union of several timelines. If you have timelines T1 through Tn and you want to talk about their union, you just do the obvious thing. You take the union of all of your temporal assertions, you take the union of all of your constraints. Okay? So one property that is important is consistency. If you have a timeline or if you have a union of several timelines, well, remember this has some uninstantiated variables in it, so we can take ground instances of it. All right? So suppose we have a ground instance. That ground instance is consistent if these temporal assertions satisfy these constraints. Okay? And if every one of the state variables has at most one value at a time. Okay? So that's a constraint that you have to satisfy that's not actually listed in C. The original timeline, TC, is consistent if it has at least one consistent ground instance. Okay? So here's an example of a consistent timeline. Over this time period, the location of robot R is loc1. Over this time period, it changes from loc1 to loc2. And we have constraints saying that this time point, well, these time points all four come in that order. So there's no conflict between this and this. All right? Well, now we have the same assertions as before. We have a new constraint, something saying that this location and this one are different, and we've removed one of our time constraints. We no longer are requiring T2 to be less than T3. In this case, T2 might be less than T3, in which case you're still fine. So this thing does have at least one consistent ground instance. Therefore, it's consistent. But it is not secure because there also exists a ground instance that's not consistent, in which this thing comes before that. And in that case, the robot has two locations at once. Okay? Any questions so far? All right. Security. Our timeline is secure if it is both consistent, what I just said, and if every ground instance that satisfies its constraints is consistent. Here's an example of a timeline that is secure. We know that it has at least one consistent ground instance. I think I showed you that a moment ago. Furthermore, no matter what ground instance you take, it's going to be consistent because it's required that the time points are in this order. Therefore, there cannot possibly be any conflict between that and that. Okay? So as long as these constraints are satisfied, we're fine. Here's one that is consistent but not secure. And again, it's the same one I went through before. It has one consistent ground instance, has another one that's not consistent. Okay? Okay, so if we have something that is consistent but not secure, we can make it secure by adding something that's called a separation constraint. The idea here, for those of you who know plan-space planning, is that this possible conflict is like a threat in plan-space planning, where two things can interfere with each other. All right? And making it secure, getting rid of the threat, that's like a resolver in plan-space planning. Okay? So the things that could get rid of the threat in this case would include, we could specify that R, this robot here, is a different robot than that one is, and therefore there's no conflict with this being at one location and this being at the other. We could say that this time point T2 is less than T3, and now we've moved these two intervals so that they're no longer specifying different things at the same time. Or alternatively, we could say that T4 comes before T1, and so that interval comes before this one. All right? Or we could say that T2 and T3 are the same, and that this location is the same as loc 1. And so now what we have is the robot staying at this location for a while and then starting to move. All right? Or finally, T1 and T4 could be the same, and L prime could be the same as loc 1. All right? Any questions about that? Okay, so those are all the possible resolvers in this case. Causal support. The idea, well, let me go through the example first. Suppose we have a temporal assertion that either says this, in other words, that over this time interval, robot R1 is at loc 1, or says this, over this time interval, the location changes from loc 1 to loc 2. All right? Well, what both of these things specify is that at time point T1, the robot is at location 1. There and there. Okay? So one question you might want to ask is, if this robot is at location 1, how did it get there? Well, we have some notion of physical causality in our heads. It says it had to get there somehow, but we don't know how. This is like an open goal in plan-space planning. It occurs, we need something that makes it occur. So causal support for a temporal assertion is something that establishes the condition that holds at the beginning of that temporal interval. All right? So something that puts the robot at this location T1 so that it can either stay there or start moving elsewhere. Okay? So that's going to be one of two things. Either another temporal assertion that ends at this time point T1 with the robot being at location 1. Either it's at location 1 over the entire time interval, or it ends up at location 1 at the end of the time interval. Okay? Except in that case, then you need to say what's the causal support for those. The other possibility is we can say, simply accept it because I say so. We might have information at the beginning of our planning problem telling us that a particular one of these things is supported a priori. All right? So these temporal assertions that we might use, those again are like resolvers in plan-space planning, things that we use to take care of the open goal. Okay? All right. In plan-space planning, no, sorry, I'm getting ahead of myself if I say that. Let me go through this example. We have these three temporal assertions, okay? Location of R1 over this time interval, over this time interval, and over this time interval. Well, This second time interval, alpha 2, provides causal support for that one, because this one needs the robot to be at location L starting at time t3. This is what gives it to us. All right? Similarly, this temporal assertion provides the causal support for that one, because it puts the robot at location L at time t2. For this one here, we don't have any causal support. Well, a timeline, the entire timeline is causally supported if every assertion has causal support. All right? There's 3 ways that we can add causal support for an assertion, and these are like different ways that you could put in a resolver in plan space planning. Okay? So the first way is we could put in a persistence condition. If this thing establishes we're at this location, it should have said, this is another error, I'm sorry. This should be loc 2 here, this should be loc 2 here, this should be loc 3 here. Again, I will fix that. This establishes that we're at loc 2 at this time point. This requires that we be at loc 2 at this time point. We could simply put in a persistence assertion saying this thing didn't move. All right? It's a body at rest, and so it tends to remain at rest. Okay. Another possibility. Sorry, I didn't finish this. This provides the causal support for the second temporal assertion, and it itself is supported by the first one. So that takes care of the problem. Okay? The second way that we could do it is add a constraint. Something saying that T2 and T3 have to be the same time point. And in that case, we're changing something that looks like this to make it look like that. Okay? So now this thing is causally supporting that. And again, another resolver. The third way we can do it is to add a change assertion. If we need to be at this location, loc 3 at time t3, and we're at loc 1 at time t2, we could add an assertion saying that the location changes. Well, the location of an object, we're assuming, is not going to just spontaneously change. If you're going to add something to make it change, it has to be an action. Well, I haven't talked about our temporal representation of actions yet, so I'm going to do that next. An action, or we're also going to call it a primitive task, is going to be, lecturing makes my throat hurt. Sorry about that. It's going to be a triple. A head, which is the name of the action and its argument list, and a set T, which is a union of one or more timelines, and a set of constraints. Okay? That's all it is. Except that there also are going to be 2 additional arguments that are not actually listed in this argument list, but we're always going to assume they're there anyway. That's a starting time and an ending time. Okay? So here's a few examples. Robot enters loading dock D from an adjacent waypoint W. All right? That's what we want to do. The way that we're going to represent it temporally is like this. The assertions are that from the starting point of the action to the ending point of the action, the location of that robot changes from waypoint W to loading dock D. And also, between those same 2 time points, the occupant of loading dock D changes from nothing to robot R. Well, you might ask, why do we have both of these? Aren't they redundant? Well, the reason why is that we're going to enforce a restriction that a loading dock is only big enough to accommodate one robot. Okay? And in order to enforce that restriction, you need to talk something that talks about whether the loading dock has an occupant or not. Okay? All right, so the constraints are this action is going to take at least 3 time units, and the waypoint and the loading dock need to be adjacent. Okay? Any questions about that? Okay. Leaving is the opposite thing. Same idea, except that the changes are in the opposite direction. Location of the robot changes from D to W. The occupant of D changes from R to empty. This one we're going to say takes 2 time points. All right? Why is it this one takes 3, this one takes 2? Number 1, I just want to show you can have different numbers in there. Number 2, you could reason that it may take a little bit longer pulling into the loading dock because you need to line the truck up with the loading dock in order for it to be useful. Okay? Anyway, so finally, navigate from waypoint W to waypoint X. They need to be connected to each other, so that's a constraint. The thing is only one assertion this time, and that is the location of the robot changes from W to X. Okay? Those are going to be the only actions that we have. We can't pick up anything. All we can do is move around. All right? We're also going to have tasks. The task of moving a robot moving a robot to a dock D. Refinement method, little bit like the refinement methods we had before, but again, everything is temporal. Has a task, has a refinement, has constraints. Well, where are the preconditions? We had preconditions before. Where they are here, remember, each of these things is going to need causal support. All right? So we have some things that look like preconditions there. These also would be preconditions, but they're basically rigid ones. If they're not true, then you're not going to be able to do this action, period. Effects are also encoded into the temporal assertions because something like leave is going to involve some changes in the thing. Okay? What we don't have that we had before. Before, the body of our method was a program that we execute. Remember, that carried some complication with it. This gets complicated enough already. We're not going to have a program on top of it. We're just going to have a list of actions or tasks. Okay? So this part of it is a little bit like HTN planning. Okay, so this refinement method says basically these 3 tasks need to occur over this period of time, and we have some constraints on the ordering of the time points. This needs to be less than this. This needs to be less than or equal to that. This needs to be less than or equal to that. This needs to be less than this. This needs to be less than this. Okay? All right. A chronicle, which is going to be a representation for a bunch of different things, is going to consist of a set of tasks, things like this. It could include primitive tasks or actions. It's going to contain a list of temporal assertions that we are saying are supported a priori. It's going to contain a list of temporally qualified assertions that are not supported a priori, and so those are going to give us some open goals, and finally some constraints. Okay? So, the chronicle can include information about current state, future predicted events, tasks to be performed, assertions and constraints to be satisfied. It can represent a planning problem. It can represent a partial or a full solution to a planning problem. And you'll see that as I go through an example. So our initial chronicle we're going to start with is, let's see, do I have it on the next slide? I'll go through it here. I should have gone through it a minute ago. We're going to have these 2 tasks, move R1 from D1 to D2, move R2 from D2 to D1, those 2 tasks. They have to occur over the same time interval. We have 2 things that are a priori supported, so they're in this set here. Namely that this robot starts out at this location, this robot starts out at this location. Okay? And then the obvious constraints. The starting time has to come before the ending time, and we have some constraints on what things are adjacent to what other things. Okay? All right, so next I'll talk about an algorithm that handles this stuff. That's called Templan. The input to it is a chronicle. An analogy here, again, to partial order planning. If you have a partial order planning algorithm, what is the input to it? Anybody? Yeah, it's or sometimes called a dummy plan. You have an initial state, you have a goal state, your goal state has got a bunch of open goals, and you need to put in stuff in between. All right? This is a generalization of that, okay? A chronicle. And in partial order planning, the partial plan had flaws. We have flaws here. The partial order planner would choose resolvers. We choose resolvers here. So it's a fairly straightforward generalization. The devil is in the details. Okay, there's three kinds of flaws that we can have. One is a non-refined task. That's like a task in SERPE. A resolver for it is to apply a refinement method or an action definition. An unsupported assertion, that's like an open goal in plan space planning. We need to add causal support for it. And finally, possibly conflicting assertions. Those are like threats, and we need to put in separation constraints. Okay? So, here's the initial chronicle. I went through what it was earlier. Here's a graphic representation of it. Robot 1 has this task, Robot 2 has this task. Okay? So our flaws are we have two tasks that are not refined. So the algorithm would refine them one at a time. I'm going to do them in parallel simply to make things go faster. Okay? Where I was when the break started was I was just about to go through this example with taking a chronicle and coming up with a complete plan out of it. So we have a chronicle that looks like this. Basically what it has in it is two non-refined tasks, the two move tasks. And I'm going to apply the move method to both of them. And just a quick reminder, here's what the move method looks like. It takes the move task and decomposes it into a leave, a navigate, and an enter. All right? So we apply that twice. And we end up with two copies of this, one for Robot 1 and one for Robot 2. And I have color-coded these things to try to help you keep track of them. Okay? So these three are for Robot 1, these three are for Robot 2. Okay? Well, now we have a bunch more flaws. We resolved 2, but this introduced 6 flaws because each one of these is a non-refined task. So we need to take care of them. Each one of these actually is an action. Remember, an action sort of goes into this task list as well. And so we're going to resolve these leave ones by applying the action definition. The action definition for leave does that. What we did was, in order to leave, the location of the robot changes from a loading dock to a waypoint, and the occupant of the dock changes from the robot to empty. And here it is for R1, here it is for R2. Okay? So let's now, sorry, I got ahead of myself. We now have only 4 unrefined tasks, but we also have 4 unsupported assertions. Let me take care of the remaining unrefined tasks, and I'll just do all 4 of them at once. We have 2 navigates, 2 enters. We take care of both of those. That puts a whole bunch more things into the assertions. Here we have the Robot 1 going from W1 to W2. Here we have Robot 1 going into D2. Here we have Robot 2 going from W2 to W1. Here we have Robot 2 going into D1. All right? So we have 10 unsupported assertions and 2 possible conflicts. I'll explain what the conflicts are later, but let's right now take care of the unsupported assertions. These 2 leave assertions, we can support them using this information that was in the initial chronicle. We were told that robot R1 starts out at D1, robot R2 starts out at D2 at time T sub S. Well, that's when these start, so these are automatically supported by those. All right? So we can move those red ones into the supported list, which I just did, and I'm going to indicate it graphically by putting the solid line there. Okay? Next, we're going to support the navigate task, and the way that we're going to do that is by constraining these 2 time points to be the same and these two time points to be the same. All right? So we do that. That moved the green ones into the supported list. It also introduced a few more constraints saying T1 has to be equal to T2, T5 has to be equal to T6. Okay? Next, we're going to support this with this. That means setting these two time points equal, and then the same thing down here. So we take all of these blue ones, we're going to move them into the supported list. And again, we did that by setting some time points equal to each other. Okay? So at this point, I can talk about the two possible conflicts that I mentioned. At time T5, sorry, where is T5? Yes. T5 is the point when robot 2 finishes leaving dock 2. And again, yeah, I think, I swear I fixed these errors. Doesn't matter. If the idea is that if robot 1 starts entering dock D2 before robot 2 has left dock D2, then the value of occupied or occupant of D2 is going to have two values at the same time, robot 1 and robot 2. Okay? That's what the occupant thing is for, is to enforce the notion that there can only be one robot in the dock at the same time. So we need to set this time point to be, this time point to be after this one, all right? And if we do that, that introduces a constraint there. Furthermore, we need to do the same thing. If this thing starts entering D1 before this thing has left D1, we have another possible conflict. And so we need to make this thing come after that thing. So we add a time constraint for that. If we add both of them, then we have a time constraint that looks like that, another one that looks like that. They're over there in the chronicle, and now we're done. We've taken care of all of the flaws. Okay? So what has happened is that neither one of the robots could enter the other loading dock until the other robot had left. But since they can each be on the road at the same time, each of them, through its action, could support the other's action. All right? Okay. So next, speeding up Templan, which is the algorithm that does that. And we're going to do that through node selection heuristics and some ways of detecting constraint violations in advance. The ideas for the node selection heuristics, some of them are similar to those in constraint satisfaction problems. For flaw selection and resolver selection, they go by different names in the constraint satisfaction literature, but basically we want to select the flaw with the smallest number of resolvers, and we want to choose the resolver that rules out the smallest number of resolvers for the other flaws. Okay? So those are the heuristics there, and again, I know I fixed that problem. There's some more advanced heuristics that have been in some publications recently, but I'm not going to talk about them. Detecting constraint violations, the idea is each time Templan applies a resolver, it modifies the chronicle, and some of the resolvers will make that chronicle inconsistent. Okay? It didn't happen in what I was doing because I was careful about what I was doing, but it can happen. When Templan changes the set of constraints, we can modify it to check consistency. Put it right into here. And if the constraints are inconsistent, then what that means is that below this node in the search space, there cannot possibly be any solutions. All right? And so in that case, we can prune that if we're doing an A-star search, or we can backtrack if we're doing a backtracking search, or whatever. Okay? Notice I only said we're going to check whether C is inconsistent. one could try to check the temporal assertions. That gets more complicated. Checking C is a little bit easier. And it's not going to detect all of the inconsistencies, but it's going to detect some, and that's going to be a big win for speeding up the algorithm. Okay? All right. So C contains two kinds of constraints. There's object constraints and there's temporal constraints. Let's assume that they are independent of each other. So that would include things like a particular time point depending on the value of some state variable. Okay? So if we do that, then we've separated these things into two separate subproblems, namely checking whether the object constraints are consistent and whether the temporal constraints are consistent. And C is going to be consistent in this case if both of them are consistent. Okay? So object constraints, and checking their consistency is a constraint satisfaction problem. Those are known to be NP-hard. You can write an algorithm that is complete but runs in exponential time. If there's an inconsistency, it would always find it. It might do a lot of pruning of the search space, but it's going to take a long time to run. You're better off using some of the techniques that would detect things in polynomial time but wouldn't detect all of them. Okay? So use some sort of a constraint satisfaction technique that's incomplete, runs in polynomial time. It'll detect some inconsistencies but not others. Consequence is that it might not prune as much of the search space. Rather than pruning something up here, you might go down to here before you detect inconsistencies. That's okay. You're still going to detect them eventually. It means you'll be exploring a larger part of the search space. Okay? It's basically a question of efficiency, not correctness. Time constraints, to represent them, we're going to use data structure called a simple temporal network. And that's a network of constraints on time points. And we can modify templan to create the initial temporal network from the constraints in C, check the consistency of that network in order n cubed amount of time. Every time C changes, to update the network and check the consistency again. And if you do this incrementally, I think that'll run in time n squared. So this is something that can be done pretty efficiently. So every time you transform this, you would update the temporal network. If it's inconsistent, then you return failure. All right? Okay. So to represent time constraints, we have simple network of time points. It looks something like that. What is it formally? Well, it's a pair VE, where V is a set of temporal variables, and E is a set of arcs connecting pairs of temporal variables. Each arc from time point ti to tj is labeled with a time interval, which we're going to call r sub ij. And what it does is to represent the constraint, saying that the difference between ti, which is the bigger one, and tj, which is the bigger one, and ti, which is the smaller one, that has to be at least a and at most b. That's what that thing means. Okay? Or equivalently, you could negate things and reverse the direction of the inequality, but big deal. If we want to represent unary constraints, we could do that also. The way that you do that is to introduce some dummy variable that I'll call t naught that has the arbitrary value 0. And now, if you have an arc r sub 0i between time point t0 and ti, if it's labeled with ab, that represents the constraint that ti minus 0, in other words, just ti, is at least a and at most b. All right? So a solution to a simple temporal network would be where you have an integer value for each one of the time points and all of the constraints are satisfied. The network is consistent if it has a solution. It is minimal if it has the property that for every arc with an interval AB, and for every time point within that interval, there is at least one solution such that the difference between ti and tj is that time point. Okay? So, in other words, these time intervals aren't any bigger than they need to be. They've been shrunk to a point where if you tried to make them stricter, they would be excluding solutions. So operations that we can do on temporal networks. One is intersection. If you have two constraints on the same time points, one Rij going from Aij to Bij, the other one R prime Ij going from A prime Ij to B prime Ij. So we're saying that this thing has to satisfy both of those. Well, you just take their intersection. We can infer that the difference between Ti and Tj is the intersection of those two time intervals, which is going to be the interval going from the maximum of these two time points to the minimum of these two time points. Okay? You can do composition, and the idea there is, suppose let's pretend for a moment that you don't have any constraint between Ti and Tj, but you have a constraint between Ti and Tk, R sub ik, and one between Tk and Tj, R sub kj. And here they are. Well, what we can infer from that is that the time interval from Ti to Tj is at least the sum of these two A points, and at most the sum of these two B points. The idea there is that if this takes time A, and this takes time A prime, then the distance between those two is going to be A plus A prime. Okay? And so we're taking the sum in both of those cases. All right? Next, consistency checking. Suppose we have something where we have time constraints on all three of these. Then what we can do is we first can compute the composition of this and this, and so we get a new time interval, which is that. Okay? Now we take that new time interval and our old one that we already had on Ti and Tj, and we take their intersection. That becomes a new constraint on that, which is basically shorter than both of those. So we've shrunk that one. Okay? So as an example, suppose we have this. All right? So if we take the composition of this and this, 1 plus 3 is 4, 2 plus 4 is 6, so the composition is 4, 6. All right? Well, we already had a 2, 3 here. We have a 4, 6 here. We take the intersection of those two, it's empty. What that tells us is that this is inconsistent. There's no way that you can come up with time points that satisfy all three of these time constraints. Okay? Well, now suppose that this interval, instead of being 2, 3, it's 2, 5. All right? In that case, we can compute our 4, 6 again, intersect it with 4, 5, with 2, 5. We get 4, 5. We then update this thing to get 4, 5 there. So now we have our new temporal network in which we've shrunk the value of that interval, and this thing is consistent, and furthermore it's minimal. If you shrink any of those any further, you would be excluding some solutions. All right? Okay. So there's an algorithm for doing this, the path consistency algorithm. It basically does consistency checking on all triples in a network. If you have a network that's more complicated than this, well, here I had one that was a little bit more complicated. You could get to much more complicated things than that, and just run this on all triples. All right? And it does that same computation that I just showed you, computing the composition and then the intersection on all of these triples. Either it will detect that the network is inconsistent, or it'll make it minimal. Okay? You can modify this algorithm to make it incremental, so that if you have as your input an STN that's already both consistent and minimal, you can add a new constraint to it, and you can check the triples involving that constraint in time order of n squared. Okay? So when I said that you could create the initial STN in time n cubed, that would be this algorithm, and then update it in time n squared, that's what I was talking about. All right? Okay, so you do that check, you can prune parts of the search space that way, that can make the algorithm run faster. Next, I'm going to talk about controllability. Suppose that Templan gives you a temporal network and you want to perform it. Well, you have constraints on the time points, and those give you some intervals during which you can start some of your actions, and you need to reason about when do you actually want to start them. So we're going to use this simple example here. The idea is, suppose that we have a robot that is going to do an action called bring and move. Basically, it's going to bring this container here, and then it's going to move into a position to be attached to the loading dock. All right? And then once it has done that, the crane is supposed to pick up this container and move it elsewhere to make that thing clear so that presumably can put that on top of it. Okay? So what we have is this thing that involves the bring and move action and the uncover action. All right? Well, suppose that we don't want either the crane or the robot to wait long. And so what we want is a difference of at most 5 seconds between the time that the bring and move ends so that the crane is done and the time that the uncover is done so that the robot isn't waiting long. Okay? Well, we now have 3 sets of constraints. We now want to choose time points that will satisfy all of them. Suppose we use the path consistency algorithm. Well, we get a minimal and consistent network which looks like this. Well, that would work if we could choose all 4 of the time points. Well, what are these time points? This says that bring and move takes at least 30 and at most 50. Once we start the action, we don't know how long that action is going to take. It may depend on road conditions or something. All right? What we do know about it is it's going to take at least that amount of time and at most that amount of time. We can choose the starting time for it, but the ending time is going to be whatever it turns out to be. All right? Similarly with uncover, it'll take between 5 and 10 units of time. We can choose when it starts, but we can't choose when it's going to end. And what we want to do is choose the starting times for both of those such that the difference between these two is at most 5. All right? Okay, so that is what I just said. Formally, what that means is that T1 and T3 are controllable. T2 and T4 are contingent. Okay? And they're random variables. They're known to satisfy certain constraints, but beyond that we don't know. So it turns out in this example we cannot guarantee that all the constraints are going to be satisfied. And I'll go through a couple of examples to illustrate that. Suppose we start bring and move at time 0, all right? And suppose this one takes 30 seconds, this one takes 10 seconds. Well, if this one takes 30 seconds, this one takes 10 seconds, and if we want the difference between these two to be at most 5, then that tells us that we want to start T3 between now I forget my own math. Sorry about this. Okay, it's just dealing with half of the inequality. We need to start this thing before time 25. The reason is that if we started at time, say, 30, and if this takes 10 seconds, then it's going to end 10 seconds after this thing did, because this thing ended at time 30. All right? If we start this at time before 25, well, neither of the actions is finished yet. I was assuming, suppose that they take this amount of time, but we don't know that they're going to take this amount of time. So it could be the case that this thing, instead of taking 30 seconds, takes 50 seconds, and this thing, instead of taking 10 seconds, takes only 5 seconds. And now, again, we end up with a time interval that's too big. All right? So in this example, no matter what values we choose for those, we can't guarantee that it's going to work out. All right, so the way we'll handle this is by using something called a simple temporal network with uncertainty, in which we have the time points divided into the controllable ones and the contingent ones, and the edges, the constraints, divided into the controllable ones and the contingent ones. The controllable and contingent ones, well, what does that correspond to in terms of our physical interpretation? The synchronization between two starting times is controllable, all right? The duration of an action is contingent. The synchronization between the ending points of two actions is contingent. The synchronization between the ending point of one action and the start of another, that is going to be controllable if the new action starts after the old one ends, or it's going to be contingent if the new action starts before the old one ends. All right? So what we want is a way for the actor to choose time points in V that guarantee that the constraints are satisfied. All right? And that has to be true regardless of what happens with these constraints in V tilde. Well, the network is strongly controllable if the actor can choose values for V such that once it's chosen those values, regardless of what V tilde turns out to be, will be successful. All right? If that's the case, then you can choose those values offline and it's going to work, period. All right? That's strong controllability. It's weakly controllable if the actor can choose values such that for at least one choice of V tilde will be successful. What that means is that you can choose these only if you know in advance what these contingent values are going to be. And I was arguing earlier that you don't know that. All right? What we want is something called dynamic controllability. That is that we can choose the values for V online by observing the things that have happened so far. That's going to give us partial information about what's in V tilde. All right? And in some cases you can control things dynamically even if you can't control them strongly. All right? So there's an how do I want to put it? There's actually a game theoretic interpretation of this. It's like you are playing a game against the environment. All right? And what you're trying to do is to get all of the constraints to be satisfied. And you're going to do that by choosing starting points for your actions that fit within the time intervals. And if you can do this in such a way that everything is satisfied, you win. All right? What the environment is going to do as your opponent is it is going to try to choose ending times for the actions that make things not turn out. It's got to choose ending times that are within the constraints for how long these actions are going to take. But the environment might be able to do so in such a way that you can't choose starting times that will work out. And if that happens, then the environment wins. All right? So if what we want is a strategy, which is basically a technique for choosing our moves based on what we've seen so far, that'll work regardless of what strategy the environment uses. That's the basic idea here. You choose time points. Here's the way the thing works, the game works. You choose time points that you can trigger at time t without violating any synchronization constraints. Simultaneously, the environment chooses time points that can be triggered without violating any duration constraints. They trigger the time points, remove them from these sets. The history is a record of all that's happened. You fail if, failure occurs if any of the constraints are violated. All right? Success occurs if you haven't violated any of the constraints and if you've gotten to the point where nothing is left. All right? So a dynamic execution strategy for both the actor and agent are things that will choose the next thing that you do based on the history of things that's happened already. All right? All right. So as an example, I'm not going to give you the algorithm for choosing that, although there is some stuff about that in the book. Actually, do I say something? I say a little bit about that. Okay. Instead of a single bring and move task, suppose we have two separate bring and move tasks. So here's the duration on bring, here's the duration on move. Well, in that case, there is a dynamic execution strategy that'll work. The idea is you start this action going whenever you want, you wait and observe this one, all right? You trigger this one at any time point within that interval. So now you've triggered it. And now you wait 10 time units and you trigger this one, all right? If you do that, well, this is going to end within times 15 and 20 after you trigger this one. This is going to end within times 15 and 20 after you trigger this one. So the difference between the two of them is going to be at most 5. All right? Okay? Okay, so dynamic controllability checking. How do you check whether something is dynamically controllable? It's an extension of consistency checking. The temporal constraints in this thing correspond to an STNU. Templan can keep this thing dynamically controllable using the incremental version of PC. If PC, path consistency, reduces the size of a contingent constraint, remember, it's always going to reduce constraints. If one of them turns out to be a contingent constraint, then it turns out that your network is not dynamically controllable. And so in that case, you can prune that path in the search space. All right? Otherwise, there's a further test of dynamic controllability that you can do that gets more complicated, and I'm not going to talk about it. Okay? But the basic idea is that you can incorporate this into Templan, and in doing so, what it will come up with is a chronicle that's guaranteed to be dynamically controllable. All right? Okay, so acting with executable primitives. Templan's actions. The idea is that we are having Templan plan with things that we called actions or primitive tasks. From the viewpoint of the actor, Ray, those things may not necessarily be primitive tasks. Remember, I talked about planning happening at the upper levels of the hierarchy and acting happening at the lower levels. This is an example of that, where we're planning with things that were abstract, and Ray has further decompositions or refinements of them. Okay? So we have the Templan action has a descriptive model, and then for that thing that was an action up here, it's going to be a task that has an operational model down here. So there they are. Templan action, leave. How are we going to leave if we're doing an array? Well, what does this say? We're going to wait now I don't remember why I had this. Never mind, the details don't matter. This was some of Malik's code, and I should have looked at it more carefully before I started to present it. I apologize about that. I don't think the details matter for what I'm going to do. The point is that this can decompose into something that involves a bunch more steps, even though it looked like a single step up here. Okay? All right. Another example, unstack was, we had a descriptive model for that up here. Here, again, you might get into the details of locating where your gripper is going to grasp, moving to that position, grasping the thing, checking to make sure you have a firm grasp, lifting, so forth. All right? You can just put that into Ray, and Ray is going to execute these. It doesn't know about the time points. It just knows when it's been asked to do something. All right? And so something in the chronicle that has a time schedule assigned to it, that would be one of these external tasks that you could put into Ray. All right? So the advantages of this are you get simple online refinement and avoids breaking down the uncertainty of some of these things that are contingent. You can augment it with the temporal monitoring functions that Ray has. However, it doesn't handle the temporal requirements at the command level. If you have concurrency synchronization or something like that, it won't handle that. You can augment Ray to include temporal reasoning. We can do that and call it E-ray. One essential component of that I'm going to say a little bit about is a dispatching function. And basically what this amounts to is taking that same notion of dynamic controllability and propagating it down into Ray, so that Ray can reason about some of the temporal constraints. All right? So dynamic execution strategy controls when to start each action and triggers it. And I have an involved example here. I think I am going to skip it, however, because it's the same idea that I went through before of choosing the starting times for the actions so as to get the constraints to be satisfied. Okay? It'll just take a lot more time, and it won't illustrate anything new. It's just the same thing at a lower level. All right? So the dispatching procedure, there it is if you want it. I will skip that as well. Suppose something happens, something goes wrong, that makes it impossible to start an action on time. Well, you have several options. You could stop the delayed action, look for a new plan, let the delayed action finish, try to repair the plan by resolving some of the violated constraints, extending a time deadline. Or let the delayed action finish and then try to repair the plan some other way. Okay? Partial observability, I think I'm going to skip that part as well, simply because I'm not as familiar with that part as I wish I were. Malik would be able to talk about it, but I'm afraid I'm going to botch something. Okay, so summary. Timelines, we have temporal assertions, constraints. I talked about conflicts, consistency, security, causal support. Chronicle, which is the union of several timelines, as well as some tasks, and consistency, security, and causal support of that. Actions, represented by chronicles. Planning problems, represented by chronicles. The flaws that you can have, how to resolve them, and they can use it, therefore, to represent partial plans and solution plans. Planning using Templan, which is like plan-based planning, except it has all the temporal stuff in it, as well as tasks. How to manage the constraints. And then finally, some stuff about acting and dynamic controllability. All right? Any questions about any of that stuff? Okay. Give me just a moment. All right, so next is non-deterministic models. I talked earlier about how things can go wrong when you're executing actions. That would be an example of non-determinism. Basically, non-deterministic action is one that has more than one possible outcome. In some cases, I made this point earlier, some cases we can choose simply not to model that as a design choice. And then we can use some of those deterministic stuff that I had in part 2 of the tutorial. The idea there would be that you take whatever the nominal case is, whatever you expect to happen if things go well, model that, and then at acting time resolve things, recover if it turns out differently. All right? Okay, well, in some cases, non-determinism is essential because there's no clear nominal case. Like that, or like that, or like that. Here, I think the source of the non-determinism is obvious. Here, it may be somewhat less obvious, so I want to talk about that one in a little bit more detail. First, what is this? Well, this is a harbor. I think it's probably Bremen Harbor. And it doesn't matter, though. It's a large harbor. A lot of containers come in, and things need to be done with them after they come in. Okay? It has a huge state space. There's probably thousands of containers here. And the number of different configurations that they could be in is going to be at least n factorial. it's a busy location. There's a lot of exogenous events happening, ships arriving, orders coming in, so on. Many possible outcomes for some of these things, and there's no clear nominal case, all right? Simply because you don't know what these things are. Even if they are deterministic, you don't know what they are in advance. An individual actor is going to know very little about the current state. For example, if it's a robot vehicle like this, you might be able to do sensing in order to identify the containers that you're looking at, but you may know very little about what's elsewhere in the harbor. Okay? Sorry. When I was adapting these slides, I didn't realize that some of them had animations on them. Oh well. All right. So let me give you a simple example, one that some of you may be able to relate to, because I ran into it yesterday, and some of you might have as well. This is the door to one of the workshop rooms, all right? This is the other side of the door. Both of them have pull handles on it. Does this thing pull in both directions? No. If you pull on the wrong side, it's not going to work. Oh, which is the right side to pull on? Which way do doors normally open into a room? Normally they open into the room, right? No. This one opens outwards rather than inwards. So I was trying to get out of the workshop room. I pulled on the handle, nothing happened. I figured out I needed to push on it. All right? And there wasn't any label to tell me that. So here are some ray methods for same thing. At the top level, we have the task of opening the door. All right? And what we're going to do is we're going to try pulling, just like I did. And if that opens the door, then we can go through it. Otherwise, we have a task called pull-push. And that basically is a non-deterministic choice that you can make between whether to use this method that tries pulling again or something that tries pushing on it. And depending on your mood and depending on whether you think that this is something that really should open that way, you may use one or another of these. Okay? All right. If you do this and it works, you can go through the door. Otherwise, you again have the pull-push task. Likewise here. Except here, there's actually a third option that I left out. Suppose it's a door that might pull, might push, or might slide. Well, what we're going to do here is if we tried both pulling and pushing and it didn't work, then we're going to try sliding it. All right? So push-slide task, and we do that. Okay? So if we take all of the various execution traces that can be developed using those methods and map them all out, what we end up with is this thing here, all right? And what's going on is the grasping on the thing. Well, you know, maybe our robot has a somewhat unreliable gripper, and so when it grasps, either it won't grasp firmly or it'll grasp okay, all right? Once we have it grasped, we need to pull, and either it will open the door or it won't. At that point, we have a choice. We can either retry the pull or we can try pushing. So anywhere that an arc is drawn like this, it's the possible outcomes of the action. All right? Anywhere that we have a couple of possibilities like this and this that don't have arcs between them is two different possible actions. Okay? Notice some of you are probably used to dealing with MDPs where you have probabilities attached to this. There aren't any here. Why? Anybody have any ideas? Yeah.
Well, in the real world, there is exactly one option that will be true. We just don't know it.
Yeah, we don't know it. And we don't really know what the probability is. In a lot of cases, you don't know it. All right? And furthermore, even if you do know it, sometimes what you might be interested in is not maximizing expected utility, but rather guaranteeing a certain kind of outcome. Even if it is lower expected utility than something that might have a probability of that's high of getting the outcome but isn't 100% sure of it, I still might want to be able to guarantee the outcome. All right? So, okay. Non-deterministic planning domain. We have a finite set of states, finite set of actions. Applicable of S, if S is a state, that's a set of all actions that are applicable. We have the state transition function that, given a state and given an action, it gives us the set of all possible outcomes. Okay? Well, obviously we cannot use linear plans. Anybody who's worked with MDPs knows that. If you do something like grasp and then pull and then move, well, that's going to be fine if you are successful in grasping and successful in opening the door. Otherwise, it's not going to work. So what you need is something that'll take one action if you're in this state and a different action in this state. So we're going to use a policy. All right? Map states to actions. And here is a procedure for performing a policy. Remember the run look ahead? This is kind of like run look ahead. Look at the current state. While you have a state that is in the domain of your policy, you perform whatever action the policy says to perform. Look at your new current state and then keep going around. Okay? So if you put a call to a planner outside of that, then you basically have run look ahead. All right? Okay. So here's a quick example. I imagine you know what's coming with this. We have this policy. If you're in this state, then grasp. If you're in this state, then pull. If you're in this state, then move. If you're in this state, then push, so on. All right? So okay, what just happened here? This thing had two possible outcomes. Let's suppose that it ended up in this one here. So now we do the move, all right? And we've gotten to the goal. Sorry. Again, I forgot what was on the slide. This was simply showing all the things that the policy could do. I didn't even need that because you already know this stuff. All right. Here's another policy. What it does, this part of it is the same. However, in S3, what we're going to do is we're going to retry. This one, if it didn't work, it did a push. This one retries. Okay? All right. So we can now define a non-deterministic planning problem, which we have a planning domain like this, an initial state, which is going to be this one, and a set of goal states, which is going to consist of just that one goal state where we've gotten through the door. All right? Now we can talk about solutions to planning problems. Both of these are solutions. They're different kinds of solutions. Actually, what I'm going to do, in order to illustrate some things, is to get rid of that state. All right? And if we get rid of that state, then this action and that one are going to vanish. All right? So now our new initial state is that one. We've already grasped the handle, and we're going to do the rest of the thing. Well, here's a third policy that we can have in this case. This one here is called an unsafe solution. It says if we're in this state, then pull. If we're in this state, then move. It has one execution trace that will get to the goal. It has some other things where it simply will go to a state where it doesn't tell us anything to do, and we won't get to the goal. All right? So that's a policy that'll sometimes work and sometimes won't. This one is called a safe cyclic solution. What it does is it has the same part that this has in it, except it has something here saying that if this doesn't work, then retry. All right? So under a so-called fair execution, this thing would eventually work and it would go there. but it's probably not going to be a fair execution because the door itself is not non-deterministic. All right? This one is a safe acyclic solution. What it does is it looks at all of the possibilities and is guaranteed to get to a goal no matter what happens. All right? Okay, so here is a categorization. All of these things are called solutions. The safe ones include the acyclic and the cyclic ones. And here's a schema for what they might look like. And then the unsafe ones are here. Okay? There's some differences in terminology between what we use in the book and what's been used in some of the literature. What we call an unsafe solution doesn't really have a name in the literature on planning with nondeterminism. In planning on MDPs, it's sometimes called an improper solution. Safe solution, what we're calling a safe solution, has been called a strong cyclic solution in the literature on nondeterministic planning, and a proper solution in MDP literature. Cyclic safe solution doesn't really have a name in either of these. An acyclic safe solution is what's called a strong solution here. All right? Okay, some planning techniques. First of all, this is an and/or graph. These are the and branches. We need to be able to solve the problem regardless of which of these things happens. This is an or branch where we have a choice between two things. Okay? Sorry, that went too fast. Well, you already know this stuff anyway, I assume. Anybody not know and/or graphs? All right. Okay, so here's a procedure for finding unsafe solutions. What it does is it chooses an action arbitrarily. There's only one possibility here, so it would choose pull. It then chooses arbitrarily one of the outcomes of that action. All right? Whichever outcome it has chosen, it then chooses an action to perform in that state and keeps going until it either reaches a dead end or reaches a solution. So both of these, the and branches and the or branches, it is treating as non-deterministic choices. Here you have a choice of which action. Here you're making a choice of which state you're going to plan for. Okay? So this is deliberately going to plan for some states but not others. It'll provide a solution that's unsafe. All right? Well, it's not a very good solution, but it's a simple algorithm. Okay, next, finding an acyclic safe solution. We can do this by keeping track of all of the unexpanded states the way A star does. Okay? Anybody not know A star? Okay. So you have your frontier, you choose a state out of the frontier, you remove it from the frontier, you look for an applicable action. If there aren't any, then you have failed. Otherwise, you non-deterministically choose one of them. And you take the state action pair and add it to your policy. And then all of the possible outcomes of that action, the ones that are not already in the domain of your policy, you add those to the frontier as things that you need to plan for. Okay? And finally, you check to see whether your policy contains any cycles. This is a complicated mathematical expression, but basically it says, look for whether there's a cycle or not. Okay? All right. So here is something that will find safe cyclic solutions. It's very similar to the one for finding acyclic solutions. All of this is the same except for here. Here we were checking to see whether there was anything in the outcome of one of the actions that ended up being the state of a predecessor action. All right, whether there were any loops at all. Here, we're looking for whether there are any loops that we can't get out of. All right, and so we have this additional condition such that there's nowhere in this loop where we can get to the frontier. All right. Any questions about those? Okay. I'm sorry, I thought I had examples for those, but I don't. Is it okay that I don't have examples? I think I have some. Are we sure I had something? Give me just a moment. Yeah, I have examples for some other more complicated algorithms, but these are some of the theoretical basis for them. Okay. So next I want to say a little bit about symbolic model checking. Safe acyclic solutions, one way to think about them. We have the initial state, we have the goal, we have the actions that are guaranteed to get us to the goal, all right? Those are called the strong preimage of the goal, okay? This one is not in the strong preimage because it's not guaranteed to get us to the goal. So our strong preimage includes just that, okay? Now we can look at what are the things that can get us to either the goal or that state. Anything that's guaranteed to get us to one or another of those would be in the preimage of this set of states, okay? And you can keep extending that until you get to the initial state. One of the original algorithms for dealing with this stuff worked that way. One of the issues is that you end up with a backtracking search over what can be a very, very large state space. Some of the same issues arise with some of what I was just talking about. It turns out that you can deal with that by representing collections of states symbolically. The idea is that you can use simple propositional formulas to represent very large sets of states, so that instead of listing all of these states one at a time, we have the set of all states that satisfy some property, okay? And state transitions can be represented by quantified Boolean formulas. Binary decision diagram representation can be used in order to represent this stuff and manipulate it. And there are some well-known planning algorithms that work this way. Okay? I'm not going to go into the details. I just wanted to let you know that it exists. What I'm going to spend more time talking about is determinization techniques. And the idea is that it's a lot easier to find solutions if they don't have to be safe. Find safe solution needs to plan for all of the possible outcomes. Find solution only needs to plan for one of them. So the idea is, let's call find solution multiple times. So we end up with an algorithm called guided find safe solution. What it does is it finds an unsafe solution for each leaf node of that thing. If that leaf node isn't a goal, then find a solution and incorporate it into the thing. So I'll go through an example of that in a minute, but let me give you an elaboration of it first. Question is, how would we implement that? Well, we need an implementation of find solution. It needs to be a very efficient one because we're going to call it a lot of times. Well, a lot of work has been done on developing efficient classical planning algorithms, so let's leverage it. Okay? We can use all of this by using any one of those that's a complete algorithm as our find solution. Well, the way we're going to do that is through determinization. We need to convert our non-deterministic actions into something the classical planner can use. So suppose we have an action that has a couple of different possible outcomes, like pulling on the door. What we're going to do is we're going to give the classical planner a couple of deterministic actions, one for the case that succeeds and one for the case that doesn't. All right? And we're going to let the classical planner choose whichever one of those it wants to use in order to come up with its solution. All right? So the classical planner isn't going to return a policy, it's going to return a linear plan. If that plan is acyclic, then we can convert it to a policy. That policy is going to be an unsafe solution because it's only going to work on one of the possible traces. All right? The way we do the conversion, remember these actions are the deterministic ones. This one will produce some state as its outcome. I'll call that state S1. Within that state, that's where we're going to do S2. It'll produce another state S2, and so on. Basically, whichever state each one of these things produces, we use that as the state in the next state action pair. All right? Okay. So this gives us a modified version of that guided algorithm called find safe solution by determinization. The idea is you find a classical solution to your problem in the determinized domain. You translate it to a policy. Then you take the, since this is a leaf, since it's an unsafe solution, a lot of leaf nodes that aren't goals, for each one of those, you find a classical solution and translate it to a policy and incorporate it into your existing policy. And you just keep going like that until you're done. All right? There's some additional details that you need in order to handle dead ends. That gets a little bit complicated, and I'm going to skip it. As a quick example, remember we determinized the pull action into pull 2 and pull 3. All right? So the classical planner chooses pull 2, and here it chooses move, and it's now found what looks like a nice classical solution. Well, we can convert that into a policy that says if you're in S1, then do pull 2, or pull 2. Yes, I'll say pull 2 for now. And then if you're in S2, do move. And then we take pull 2 and replace it with pull. And now we have a leaf node over here that we need to plan for. So we call the classical planner on it. It comes up with push 4 and move. All right? Well, we convert that into a policy, incorporate it into our existing policy. Now we need to plan for this. We call the classical planner here. It comes up with that. We turn that into a policy and incorporate it, and we're done. All right? Make sense? Any questions about that? All right. Okay. So let me talk a little bit about online approaches. The motivation is our planning models are approximate. Execution seldom works out as planned in a real-world environment. Our large problems may require too much planning time if we're trying to come up with a policy for a large search space. Non-determinism makes the planning exponentially harder. Some of these algorithms can take a large amount of time. The same is true for MDP algorithms. So we need to identify good actions without exploring the entire search space. Well, we can use heuristic estimates. In some cases, we have domains that are safely explorable. What that means is that it is safe to create a partial plan, because no matter where we are in the domain, the goal state is reachable. So going back to here, this is a safely explorable domain. There's no dead ends. All right? No matter what state you're in, there exists a path to the goal. In other domains, you can reach dead end states. Your partial planning won't guarantee success. If we were able to plan fully, we might be able to detect those dead ends, but we don't necessarily have time for it. But if we do partial planning, we can at least avoid some of the dead ends, and that'll make success more likely. All right? So here we have an algorithm that looks like run lazy look ahead from part 2, except that it uses policies. Calls the look-ahead algorithm. The look-ahead algorithm returns a policy. If it's the empty policy, then you fail. Otherwise, you perform whatever the thing says to do until it stops telling you things to do. Basically, you keep going into states that are in the domain of the policy until you reach one that isn't, or until you reach a goal state. All right? If that happens, then you call the look-ahead algorithm again and keep going like that. Okay? Here is FS replan. This is like run look ahead. It calls the classical planner on a determinized model, converts that plan to a policy, and this is an unsafe solution. So what do I want to say about this? It determinizes the domain, calls the forward search algorithm, converts that to a policy that's unsafe, but it's going to execute it anyway as far as it can. All right? So it performs whatever the action is that it says to do in the current state, takes a look to see whether that worked out. If it does, then fine. But if not, well, it goes back in the loop and calls plan to policy again. Any idea why we chose to call that FS replan? Well, the original version of this, we simply abstracted it. This thing was fast forward, and this was called FF replan. Okay? That's what it does. You can generalize it, though. And that is that instead of calling the classical planner and turning it into a policy, you could call, as a look-ahead algorithm, any one of the algorithms that we've talked about up until now. All right? Anything that returns a policy. So it could be any one of those. If it doesn't have time to run to completion, then you could use some of the same techniques that I talked about earlier. Receding horizon, sampling, sub-goaling. You could use iterative deepening if you wanted. You could use some other technique. All right? Oops, sorry. What did I just do? All right. Another possibility would be full horizon but limited breadth, where you look for a solution that works for some of the outcomes, so that you're maybe using something like find acyclic solution, but you're modifying it to examine not all of the outcomes of your actions, but only I of them. So here we have the find acyclic solution algorithm, and instead of taking all of the things that the action produce, we're only going to take I of them, and we're going to add them to the frontier. All right? What that basically does is something sort of along that line, except a little bit more bushy, because at each state that it is going to go to, it'll take a random sample of possible outcomes. Okay? Iterative broadening is an algorithm that you can do that makes use of this. You run this successively with I equals 1, I equals 2, I equals 3, and so on until you run out of time. And so that each time you do, you presumably get a little bit better plan. How many of you are familiar with the UCT algorithm for Monte Carlo rollouts? A few of you. Any idea why UCT might be something well known? UCT was the algorithm that first, or something like UCT at least, was the first algorithm to do reasonably well at the game of Go. Ordinary game tree search algorithms did not work well because of the high branching factor. Monte Carlo rollouts did, and it was something along this line. And then UCT was used, or something again similar to UCT, was used to train AlphaGo. And I assume you've all heard of AlphaGo, yes? Okay. So you can express it, if you want, as a kind of iterative broadening where the value of I differs at each node. All right? I won't go into that. Let me see. Here is an algorithm that does a certain amount of learning. It's called min-max LRTA star. It goes around in a loop where it looks at whatever the current state is. As long as it's not a goal, and as long as there's at least one applicable action, it will apply a heuristic function to the applicable actions. Basically what it'll do, if there's several applicable actions, then for each one of them, it will look at the heuristic value of the worst possible outcome. So if an action leads to 3 states, one of which has a value of 2, another one has a value of 3, another one which has a value of 5, then the heuristic value we're going to associate with that action is 5. All right? And you do that for, sorry, I hit that without realizing it. You do that for each of your applicable actions, and then you take whichever one of those actions had the best worst case heuristic value. All right? And now you update your heuristic function at state S to say that our heuristic value for S is going to be 1 plus whatever you computed up here. Here we're assuming that each action has a cost of 1, so this would be the cost of that action plus the heuristic value of what it takes, the worst case heuristic value of where it takes you. All right? So you can simply go around your domain, choosing an action that has the least worst case cost, updating the heuristic function to use that, performing the actions, in a safely explorable domain in which there's no unfair executions that's guaranteed to reach a goal. All right? The reason this is called min-max LRTA star is there's a well-known algorithm for MDPs called LRTA star. We can't quite do the same way that it works on MDPs since we don't have probabilities. So instead of taking an expected outcome here, we're taking the worst case outcome. All right? Okay, I talked about the possibility of dead ends. An explicit dead end would be something where you can't go any farther. An implicit dead end would be one where you can get into a situation here where there's no way of getting out. All right? We get completeness only in domains that are safely explorable. The reason why is that if it's safely explorable, neither one of these is going to occur. And I thought I was going to say something else about that. Oh well. Okay, a little bit about acting with interactions. I want to go back to this problem that I had at the beginning of the tutorial about opening the door. One possibility would be our robot could ask the door how to open it. The door responds saying what kind of a door it is. The robot says, give me your opening instructions, and the door provides the opening module. Okay? Well, here, let's take a simplified version of that. We get information saying that it's a sliding door. What that tells us, if we know how to open sliding doors, is a procedure for doing it. Something that would look like this. First, grasp. Check the door type is where you find out it's a sliding door. And if it's sliding, then we do that. Okay? What happened here? PowerPoint froze. That's what happened here. Okay. Okay, so the idea is that if you can interact with other agents, they can give you information that will help you do what you need to do. And one way to model this is with what are called input-output automata. Here we have an output that goes from our robot over here to the door asking what its type is. Here we have potential inputs that the door can provide that then will tell us which one of these directions we're going in this network. Okay? And the door would presumably have another input-output automata which would get this message and which would provide one of these messages. So you can have several of these things interacting with each other in order to accomplish something. And we're going to need some way for multiple agents to communicate with each other if they're going to coordinate. So if we have a collection of I/O automata, we can't just start them running and hope that the interactions are going to work out. They may not work with each other in the way that we want them to. What we need instead is a control automaton of some sort, which will send inputs to these things, get back what they produce as output, based on that decide what it wants to send to various other automata in order to get the interaction to work out the way it should. So a trivial example of that, this same network that I just had here, a control automaton for this would be something that finds out what the type of the door is using a sensor and returns the appropriate information, either pulling, pushing, or sliding, that gets used by that. Okay? This would be the input to the control automaton. And that would be the output that it sends back to the robot. You can synthesize control automata using nondeterministic models. The idea is you take your I/O automaton, translate it into a nondeterministic planning domain, and you use and/or search and symbolic model checking or determinization in order to solve the thing. And that will give you a control automaton that is basically a policy. So it's a simple version of control automaton. All right? The translation, I'll give you a quick example of how that works. Here we have this I/O automaton. The way that it gets translated into a nondeterministic planning domain is when we are trying to sense what the distance is to the door, if we're the robot. Either it might turn out that we are too far away from it to grasp the handle, or we might be close enough that we can grasp it. Okay? Well, at acting time, we're going to find out that information. At planning time, it essentially is a non-deterministic outcome. All right? So we treat it as that. I got far and close mixed up here. This is the one where we're too far. Sorry, give me just a moment. This was one of Paolo's examples. Just an announcement for some of you who came in late. It was going to be Malik and Paolo and me presenting this thing. Malik wasn't able to make it because of some personal and family reasons. Paolo had a medical emergency. And so I'm teaching the whole thing. And in some cases, I'm not entirely familiar with their examples. So I apologize for stumbling on this one. The idea is that these inputs the inputs to the thing are basically non-determinism in our non-deterministic automata, because that's the thing that we don't know what the answer is going to be until we're actually acting. So if we're doing this at planning time, we can turn this into a non-deterministic automaton in which that's our non-deterministic outcome. All right? That's what I was trying to say. And then we can come up with a control policy by solving this thing, which is going to say, well, we do this sensing action, far or close, if we're in that state. Far or close is going to transition us either to that state or to that state. If we're in this one, then we grasp. If we're in this one, then we move. And I think move and grasp got reversed from here to here. I did not make that mistake, Paolo did. I made most of the other mistakes on this, but that one is not mine. Okay, so then if you're in this, if you're in this state, then you grasp. So the idea, no, I take that back. I was wrong when I said Paolo had it wrong. If we're in this state, we do want to grasp. If we're in this one, that's when we want to move. I got it completely backwards. He was absolutely right. The point is that we can come up with a policy that solves that. That ends up then being our control policy that we would use to interact with our I/O automaton over here. Okay? So a research challenge then is, well, this thing, how did we get it? We got it by tracing out all of the paths through this hierarchy, okay? So what we need to do somehow is to handle the hierarchy and the I/O automata at the same time. And we need to be able to do it in general. That is some ongoing research that we're doing, and we have a PhD student, Sunanita Patra, who's right here and is working on that topic. So what we have in that is refinement methods. They look something like this, in which the body, rather than being a piece of code, is an I/O automaton. All right? And so planning in a situation like that provides a way to plan for agents that are interacting with each other, where the description of the agent may be hierarchical in nature. So, summary. Using non-deterministic models sometimes is a design choice, sometimes it's a requirement. I talked about types of solutions for non-deterministic planning problems. A little bit about some planning algorithms for each. Spent a bit more time on determinization techniques. And a little bit on how to do the look ahead. And then finally how to control interactions among multiple actors. Is there any question about any of that? No? Okay. So, relation to the book, how am I doing on time, by the way? Was this supposed to end at 5? What? 5:30? Okay. I do have enough time then. Good. The relation to the book, this section was part of that chapter. Again, here's where you can download the slides as well as a copy of the book. I already asked you if there were any questions. That's the end of this. I have a brief closing, and I think that will get us right to 5:30. Okay, so the key ideas that I covered today. One is the actor's deliberation functions include planning what actions to perform, and acting, which is how to perform them. Each of these needs the other. So I talked about some principles for integrating them, including multiple levels of abstraction, heterogeneous reasoning, continual online deliberation. And the approach that we're using for that involves refinement methods. Refinement methods we can use to provide a representation for both our descriptive models, which we can use for prediction purposes, and our operational models, which we use for carrying out the actions. And they can handle different kinds of models, deterministic, non-deterministic, so on. And there's some potential for integrating specific representations and techniques. Future research. Some possibilities for things that you could work on if you get interested. Number one, better ways to integrate acting and planning. I talked about some of them. Several points I talked about things being incomplete or more work being needed. Furthermore, there's more deliberation functions other than just planning and acting. Interacting, I touched on that a little bit at the end. Learning, I think, is going to be really important for getting machines that can learn how to plan rather than just doing things that we tell them to do. Acting, we talked about today. Observing, sensing actions, that's a deliberative activity. Monitoring is another one. And reasoning about goals. The idea here is that sometimes you may need to figure out what your goals are in order to plan for them. And our planning research environment always assumes that they are given to us. They can't always be. Okay, thank you for attending.